sets up.
If it's all right, we're going to get you to present immediately after Ben, but you're just organised dinner to come out 10 or 15 minutes after everyone else's.
Sure.
Everyone's dinner will come out to start your presentation.
Yep. On that point, I'll have the chicken.
Chicken.
It's a coincidence?
Excellent. Cool. I'm Ben Schulz, and I'm a data scientist and machine learning engineer at Consilium Technology. And at Consilium, we're an organisation that consults to all sorts of different companies from all sorts of different industries on their machine learning problems and their big data problems. So we get a lot of clients coming to us that want to get involved in machine learning. You know, it's the big buzzwords, everybody's talking about it, but nobody really knows what to do with it. So we get people talking about their big data, and then we go out and meet with them, and they've got an Excel spreadsheet, and we have to try and find a solution for this. So what I want to do tonight is show you how to define a big data or machine learning problem, and I'll take you through an example of a recent client that we've dealt with to do this as well. I'm going to be walking to the clicker. So just to get everyone on the same page, let's define machine learning as the training of a model from data that generalizes a decision against some performance measure. Now, because words are boring, let's put this into a graph. So as you can see here, is a decision-making activity. This is, in machine learning speak, a model or an algorithm that we're trying to train. So machine learning is essentially if we can get that model to improve its performance as we show it more data. That's what the definition of machine learning is. So I want to introduce you to a guy that we've worked with recently, Harry the farmer. So Harry owns a bunch of glass houses that he grows tomatoes in the northern rural Adelaide Plains. Now he wants to be able to predict his yield. So his challenge is that he has a contract with a supermarket, Woolworths, Coles, whoever, and he signed that contract 6 weeks out. So he has to know what he's going to be giving those supermarkets in 6 weeks' time. So say his contract obligates him to provide them with 1,000 kilograms of tomatoes, yeah? If he produces 800 kilograms of tomatoes for that period, he loses out because the supermarkets, they're not going to be happy with him either. They're getting 200 kilograms less than what they ordered for. And on the flip side as well, if he gives them more, if he has a bumper crop and he creates 500 kilograms worth of tomatoes more than what he said he was going to do, he's either going to give them to them at a lower price and devalue his tomatoes next time he sells them to them, or he's just going to throw them out, or even try and maybe find a different seller, but that's also difficult in a competitive market. So what Harry asked us to do is to try and create a model that would be able to predict his yield within plus or minus 15%. So that's what he wants. Plus or minus 15%, he reckons will mitigate this risk for him. So what we do is, as data scientists and machine learning engineers, we sit down and we have a look at the literature, we talk to the domain experts, and what do they think will be able to inform this model. So we have things like temperature, humidity, water, area, the density of the plants, the harvest schedule, the types of fertilizers they're using, how much fertilizer they're using, the health of the plants, whether they've had a disease that's wiped out half of the crop, the plant growth measurements, so how big are the flowers, how tall are the trees, how big are the leaves, and also the resources. So if he has 10 people picking tomatoes today and he has 50 people picking tomatoes tomorrow, obviously he's going to be able to pick more tomatoes tomorrow than it is today. And in his industry, that's a possibility. And clearly also we have the measured output as well. So we have the harvest yield, which is our target in this situation. So in machine learning speak, we call this as a supervised learning problem. So there's three types of machine learning. There's supervised learning, there's unsupervised learning, and then there's reinforcement learning. So supervised learning accounts for about 90 to 95% of commercially produced solutions. Now, because this is the real world and we don't live inside a university anymore, we realise that Harry doesn't actually have access to all that data. So what he does have access to are things like temperature and humidity and water, because he measures these in his climate control system within the greenhouse environment. He has access to the area, he knows how big his farm is. He roughly knows what the density is, and we can extract the harvest scheduling from the harvest yield dates, the start and end dates. And for this supervised learning problem, we need to know a bunch of the inputs, and then we need to be able to map them to a measured output. So that's what our goal is for this task. So we look at this historical yield data. So I'm not going to show you all the input data, but this is the historical yield data, the measured output from 2010 to 2017. So you can see it looks a bit just like a clump of dots. There's just a scatter plot of harvest yields, essentially. And what we do in machine learning is we have to split this up into a training set and into a test set. So our training set is used to build our machine learning model. So roughly we take, on average for particular projects, we take a 70-30% split. So we take 70% of the data to train our model, and then we take the remaining 30% to test our model. And in many situations, you also want a cross-validation set, but for small data sets like this one here, a training set and a test set is all we can do. So we've taken all the data before 2015 as our training set, and all the data after that as our test set. And what we've done is we've had our super intelligent expert data scientists try and create some sort of model that would be able to predict Harry's tomato crop yield. So this model here uses basic regression techniques. This actual particular model uses some of the expert analysis that has been coming out of Facebook recently for their time series data. They have a lot more data, and it's seasonal as well. So things like Christmas and summer, you might get more posts than in the middle of winter when there's nothing happening. So we've used that same sort of model to apply this to Harry's problem here. And lo and behold, we were able to obtain a mean absolute percentage error of 13%, which is within the plus or minus 15% accuracy that Harry was wanting. So that's a good sign. So let's take this back to the definition of machine learning here. So we have our initial model there that I showed you just on the previous slide, and that's the 87% model. So if we use that model, we get 87% accuracy, give or take. We're aiming for 100% accuracy, aren't we? Obviously, that's the goal with all machine learning algorithms, to attain that 100%. But the question is this 13% error that we saw on the previous slide, is that all random? And of course there is some randomness to that. There's the genetics of the plant, how much light it got, how much water it got. It's all a little bit different at every time, every harvest period. But then there's also the other things that we missed out on. So the data that Harry provided us, although he had some of the data, there was also bits that were missing, and there were differing resolutions. There's a whole bunch of stuff that we could improve on to get a better result. Not only the inputs that we did have, but the ones that we didn't have as well, so like the fertilizer, the plant measurements, those sort of things. So what we've done is we've recognise that people are still the experts of their domain. So Harry is still the expert in this situation here. So we can provide him with a model that gives him an 87% accuracy, but he really wants to get that 100%. Okay, so what we do is we give him an AI tool that enables him to manipulate this base model. So for example here, average temperature and average labour. Say in the month of June coming up, Harry knows that we're going to experience a hotter than average June, and instead of having 10 people to pick tomatoes, he's going to hire another 10 people, and he's going to have 20 people picking tomatoes for him. So what we're able to do is leverage the base model that we've created and manipulate that to give him a higher accuracy model based on his expert knowledge. So this is absolutely a prime example of machine learning not needing to take over everything. We need to work with it. We've provided a prediction for Harry. We then get him to use his expert judgment to then provide access to an action, i.e. the yield forecast that he can go then and take to the customers and provide them with an accurate representation of what he's actually going to be producing in 6 weeks' time. Thank you for listening.